Hello and welcome to the second lecture of multi-user information theory. We will give a survey what we did in the last lecture. First, we look at the point-to-point connection in information theory. There, the typical picture is like this communication systems you see in figure 1. So a source output some text, let's see China's text, for example, send it to the source encoder. The source encoder want to change this, for example, in a binary sequence and put out all redundancy so that it do some data compression, then send the sequence to the channel encoder. The channel encoder now input some redundancy because he wants the sequence should be sent over a channel which is noisy. And so the goal of the channel decoder is, of course, to receive the right sequence also if the channel makes some noise. So then it's put to the source decoder who put in some redundancy and sends this to the destination. The final goal is, of course, that the error probability that the message sent from the source is approximately the same as the message of the destination, or is the same. And we observe already that we have two different goals. So in source coding, the source encoder wants to put a short sequence of bits, so his concern is data compression. The channel encoder wants to assure that the message can be transmitted correctly over the channel. So his concern is to build in some redundancy to the sequence. So that's a picture for point-to-point connections. We will look at source coding models and we will look at channel coding models. Of course, we will look at multi-user models. Like in this example, the broadcasting channel, we have one encoder, but we have two decoders. So this is a multi-user channel coding problem. We will do some information theoretic analysis. What does it mean? So because you have all attended the lecture of information theory, you know this method already. Just to remind you on the important tools. So we have h of x, which is a Chen entropy. It's a measure of information in a single random variable x. Then we have the mutual information as a measure of information in common two random variables x and y. Then we will always look at the rate of some code. It's called the code rate. It's a proportion of the data stream which is useful. Of course, the rate for channel coding, we want to have a high rate as possible, and for source coding, a small rate as possible. We look in both cases at the capacity as the supremum of all achievable rates. So the main result for channel coding is the DMC capacity of a channel W. So the capacity W is the maximum overall input distribution of the mutual information of the input distribution and the output distribution. In the information theory lecture at the top, it's proof with Gallagher method. We will see that there is another proof. It's done with typical sequences and random coding. And the idea is to find a small set of sequences which carries most of the probability and use it for coding. We introduced this new method or new proof. It's not new because already Chen used this type of proof because it can be used for many of our multi-user models. What is now a typical sequences? To understand this, we look at the discrete memberless source. The discrete memberless source, you already it was already introduced in information theory. It's a source of a finite alphabet x, and it puts out independent and identical numbers. You see here x3, x2, x1. Now we want to define when is a sequence which you receive is typical or which is put out by such a source is typical. Therefore, first we define entropy typical sequences. Now let Xn a finite sequence of length n, whose ith entry is denoted by xi and all values are in x. We write xn for the Cartesian product of x, and we have that xn is in xn. By na of xn, we denote the number of positions of xn having the letter a. And we looked at some example, and you all agree last time that intuitively naxn should be approximately n times px of a. So Shen choose now a definition which is based on the entropy. To understand this, just look at this notion here. If you look at the probability of a sequence of length n, we of course can write it as a product from 1 to n of px of xi. That's done here in another way. It's just the other notation that instead of pxn, where we write the random variable xn to the top, we write here pnx, because all n random variables are distributed equally. So now we assume, let's look at the case if the probability of a sequence is 0. Then this appears if we have a symbol a with probability 0, that means it's not in the support of px, which appears in the sequence. Then, of course, the probability is 0. Now, what can we do? We now put in our, instead of writing this product in this way, we just count the number of appearance of a symbol in xn and write pxa to the naxn. That's possible, of course. It's just some kind of renumbering. And now we intuitively guess that naxn is n times px of a. So it should be true that px of xn is equal to the product of px of a to the n times px of a. So we just replace naxn by n times px of a. And now if we look at the logarithm of this times 1 over n, then that's approximately the entropy of x that we proved last time. And now if we make this intuition more precisely by setting the random variable yi equal to minus log 2 of px of xi, we see that the expected value of yi is exactly the entropy. And now we just use the weak law of large numbers. We just use this law here and we get this here. And then you see why it's reasonable, why we define the entropy typical sequences in this way here. So we call a sequence xn typical with respect to epsilon if it fulfills this equation here. Alternatively, we can write that this is between the entropy of x minus epsilon and the entropy of x plus epsilon. We made some examples in the lecture last time, and also in the tutorial you make some examples. The main result we get then is theorem 1. So let's T and epsilon with a tilde of px denote the set of entropy typical sequences. Then we get the following result. The probability of an entropy typical sequence is approximately 2 to the minus n of h of x. So all typical sequences have approximately the same probability. The second property is that the cardinality of the typical of the set of typical sequences is approximately 2 to the n h of x, so the entropy of x. And the last property is that the probability that a sequence is in the set of typical sequences goes to 1 if n goes to infinity. Finally, we made a remark last time already that we can also generalize this, what we did for the discrete case, for the continuous case, for a continuous random variable, like we did also in the information theory lecture. In this case, we replace just the Chen entropy with a differential entropy, and we get the same results. After that, we use another notation of typical. In this case, we just count the number of a's in xn again. So we look again at n-a-xn over n. And then we call the sequence xn typical if this number for all a lies between 1 minus epsilon times px of a and 1 plus epsilon times px of a. Then we call the sequence epsilon letter typical. And again, we denote the typical set by Tn epsilon of px. And we look already at some examples, and you make it more intensively in the tutorial last week. Finally, we got the same result for letter typical sets, or similar result as for entropy typical sets. Again, we get this result, if you use this notation, that the probability that a sequence is typical is approximately, again, 2 to the minus n h of x. Again, the set of typical letter typical sequences is the cardinality is approximately 2 to the n h of x. And the probability that a sequence is in the set of epsilon letter typical sets is 1 if n goes to infinity.